All right, today we're going to tackle one of the most mind-bending and exciting frontiers in all of technology, quantum computing. We're going to get right to the heart of what makes it so different and, potentially so powerful. Let's just dive right in.
So to really get our heads around quantum computing, we actually have to start with a much bigger, almost philosophical question. What even is a computer? I don't mean the box on your desk. I mean the very idea of computation. Is it just something we humans came up with, or is it something more fundamental?
And our source material poses this really cool thought experiment. Imagine we finally make contact with aliens. Would they have computers? Now think about it. We wouldn't expect them to have invented, say, chess or Pokemon, right? Those are purely human things. But if they also had computers, well, that would imply something huge. It would mean that computation isn't just a human invention. It's a universal principle that anyone, anywhere might discover.
And that gets to the core of it. The idea that computing is literally baked into the fabric of reality. It's not a gadget we built. It's a deep property of the universe that we uncovered. So, okay, how did we get from our laptops to this massive cosmic idea?
Well, you see, our very definition of what a computer is has gone through this fascinating evolution, moving from the abstract world of math into the very real world of physics.
The whole story kind of kicks off in 1928 with a question about the limits of what math can even do. And to answer that, the brilliant Alan Turing had to first define what he meant by a step-by-step procedure or an algorithm. In doing that, he basically invented the idea of a computer, the universal Turing machine, which is the abstract blueprint for every computer we use today.
But then, almost 50 years later, a physicist named David Deutsch came along and completely reframed the whole thing. He wasn't asking about math. He was asking about reality. He asked, could we build a single machine that could simulate any possible physical system in the entire universe? See the shift? He tied the definition of a computer directly to the laws of physics.
Now, this new physical definition was a total game changer, but it also immediately exposed a huge problem, a fundamental gap in what our computers could actually do.
So here's the wrinkle. If a universal computer has to be able to simulate any physical system, then it has to be able to simulate our universe. And as we've discovered, at the most fundamental level, our universe runs on the seriously weird and counterintuitive rules of quantum mechanics.
And this is where our normal classical computers just hit a wall. They are built on Turing's abstract idea, and they are flat out terrible at simulating quantum physics. It's like trying to paint a sunset using only a black crayon and a white crayon. I mean, you might get a rough idea across eventually, but it's going to be incredibly slow, inefficient, and you'll miss all the important stuff.
So, to get past this roadblock, Deutsch realized we couldn't just keep trying to improve the old design. We needed a totally new kind of computer, one built from the ground up to speak the native language of the universe, which is quantum mechanics.
Okay, so we all know the classical bit, right? It's the bedrock of our entire digital world. It's an on or off switch. It's either a 0 or it's a 1. Simple, reliable, black and white.
The quantum bit, or qubit, oh man, that is a whole different beast. A qubit state isn't just a simple number. A better way to think about it is like an arrow that can point anywhere on the surface of a sphere. So while a classical bit can only be at the North Pole for 1 or the South Pole for 0, a qubit can point anywhere on that globe. And that seemingly small difference changes everything.
Because its state is this little arrow on a sphere, a qubit can do something incredible. It can exist in what's called a superposition, a blend of both the 0 and 1 states at the same time. It's not just in between them, it's a rich combination of both possibilities, all wrapped up in the direction that little arrow is pointing.
So this isn't just about a fancier way to store a 0 or a 1. No, this new foundation gives us entirely new rules to play by, entirely new operations we can perform on information, and that is where the real power comes from.
So how does this work in practice? Well, we use these special operations called quantum gates. Take the Hadamard gate, for example. It can take a qubit that's just sitting there in the simple 0 state, our arrow pointing down to the South Pole, and in one single step, it can flip it right up to the equator, putting it into a perfect 50-50 superposition of both 0 and 1. There is literally no equivalent to that in classical computing. It's a brand new move.
And the source material has this absolutely brilliant analogy for this. Think of it like this. Classical computers have to follow a long, winding road around a giant lake to get from point A to point B. What quantum operations do is like inventing a boat. Suddenly, you don't have to follow the road anymore. You can just cut straight across the water. It opens up these incredible new shortcuts that were completely impossible before.
Okay, so let's tie this all together. The big takeaway is that quantum computing comes from this idea of building a computer that can simulate physics. And to do that, we use qubits instead of bits. Because a qubit state is a vector, it allows for incredible properties like superposition. This lets us invent totally new operations, these boats, that create powerful computational shortcuts, letting us solve problems that classical computers would choke on.
And that brings us all the way back to that huge idea from the beginning. If computing really is a fundamental feature of the universe, and we've just now figured out how to build computers based on quantum mechanics, what else is out there? What other deep laws of physics are just waiting for us to discover them and turn them into a whole new kind of computation? It's a pretty wild thought.